Hi class, I am back for section 3.4, linear and angular speed. So again, this is another application of some of our our arc length that we've been talking about. We're going to use this in conjunction with finding speed, right? So remember that your velocity is given to you by your distance divided by your time will give you what your speed is. Okay, so let's talk about what linear and angular speed are first, and we'll develop some formulas. Okay, so suppose that you have a point P that moves at a constant speed along a radius of a circle. Okay, so you have a circle, you have a point P, and it moves at a constant rate along the edge of that circle. Okay, your circle has a radius r, and we'll call the central point O. Okay, so we have our radius. P moves at constant velocity around the circle. Okay, like a satellite around the Earth, for instance, right? And as it moves, it's creating an angle of theta, right? And as it traverses around the circle, it is covering an arc length that we will call S, right? So the measure of how fast the position of P is changing is the linear speed. So the speed that P is moving around the circumference of our circle is the linear speed, okay? So the point along the circumference, the speed along the circumference is the linear speed, okay? We will call this V, okay? V is the linear speed. So again, speed is your distance divided by time. Okay, your distance divided by time. So, because remember, distance is speed times time, right? If I'm going 60 miles an hour for an hour, that will be a distance of 60 miles, right? So it's really just the time times speed equals distance formula, moved and shifted around and solved for speed, right? So a way of representing this then, remember my distance that P is traveling is the arc length S. The amount of time is always T, the amount of time. And so that speed is going to be given by its distance, right, or its arc length, divided by the time it took for it to go around that distance. Okay. So again here, S is the arc length traced by point P, okay, at a time of T. So as P moves along the circle, okay, it's creating an angle theta, right? And so if P is moving at a constant speed, then your angle is changing at a constant speed as well. So the rate at which your angle changes is called the angular speed. The rate at which P changes is your linear speed, right? So linear speed is for the point along the circumference, and angular speed is the speed at which the angle is going, okay? So the rate OP rotates around the origin, and so the measure of how fast this POB angle is changing or growing is your angular speed, okay? Angular speed is given by this W. This W is actually called omega. It is a lowercase Greek letter, okay? You're probably familiar with the uppercase omega. You've probably seen it in things like comic books, and alpha to omega is a biblical saying. This is the lowercase omega. Okay, so omega equals theta divided by t. So again, the distance you are traveling is given by the angle, right? A small angle is a small distance. A large distance is a large angle. And you're dividing that by t. So again, it's the exact same formula, but you're just applying it to an angle instead of this distance around the circumference. Okay. So omega is the angular speed. Theta is the measure of an angle of POB, given, of course, in radians, especially since we're talking about arc lengths and things like that here. Okay, at your time t. So just to reiterate, our angular speed is omega is theta over t. Omega is radians per unit time, because you have radians per unit of time, right? Our linear speed is going to be v equals st, s over t, right? So this is your velocity is your arc length divided by unit time, right? Per unit time. But remember, what is our formula for arc length? Arc length is given by r times theta, theta in radians. So this is really v equals r times theta divided by t, right? And notice here, we have this omega formula showing up here. What is omega? It's theta over t. Okay, so my linear speed is really my radius times my angular speed. Okay, so my linear speed is my radius times my angular speed. So let's use this. Okay, so using linear and angular speed formulas. So suppose that we have a point P that is on a circle that has a radius of 10 centimeters. We have a ray, OP, that's rotating with an angular speed of pi over 18 radians per second. So let's just stop and think real quick. What do we have? I have a radius and I have my angular speed. So if I go back to my formula, I have my radius and I have my angular speed. So I should be able to find a linear speed at the moment, right? So we want to find the angle generated by P in 6 seconds. So if I want to find my angle, okay, what should I use? Should I use my angular speed formula or should I use my linear speed formula? Probably angular speed, because angular speed is given to me known, right? So I can just say angular speed is this. I have my unit time that they're going to give me, and I can now have two things that I know, and I can solve for the last one that I don't know. Okay. So in seconds, I want to find the angle generated, right? So the speed of my ray is W equals pi over 18, okay, radians per second, and I'm going for 6 seconds, and I want to find the angle. So I know that my time is 6, okay, and so pi over 18 equals theta over 6. Okay, I'm just equating the two things that I know. I know that omega is this, and I know that omega is that, so that means those two things are equal. The only thing now that I don't know is my theta value, and so I just multiply both sides by 6, okay, and 6 divided by 18 is 1/3, so this should be 1/3 pi, okay, or pi over 3. Either way is fine. Okay. So B, I want to find the distance traveled by P along the circle in 6 seconds. So that sounds like an arc length problem. So I should use my linear speed, right? So arc length problem means that I'm now talking about linear speed. So I can use my angular speed information, because remember, angular speed is part of my linear speed equation, right? So I can use those two things in conjunction with each other right now. So I want to find the distance traveled by P along the circle in 6 seconds. S is R times theta. I already know what theta is for 6 seconds. Okay, it's pi over 3. So I'm going to go pi over 3 times my radius, which again I have is 10 centimeters. Okay, so 10 times pi over 3 gives me 10 over 3 pi. But again, this is somewhat of an application problem because I'm given a distance here, right? So I'm going to talk about my arc length as a distance. So again, this comes from part A. So this is my value, and you can write an approximation here, although I do prefer exact values as is given in this example, right? So now I want to find the linear speed, right? So again, now I have my arc length, and I want to find that in centimeters per second. So again, coming back to my formulas here, okay, I want to find linear speed. I know my omega for 6 seconds. I also know my omega period, right? Omega in this case is pi over 18 radians per second. So really I just need to take this and multiply it by r to get my general linear speed. Okay, find the linear speed of p in centimeters per second. I'm already in centimeters, so I don't need to convert anything. Okay, but v is s divided by t, or 10 pi over 3 divided by 6 from part B. So I can just plug my stuff in. But notice, what is this? This is 10 over 18, which is really what I would get if I had 10 times pi over 18, which is what I said before. So they just went about it a different way. But remember, my radius times my angular speed. My angular speed is pi over 18. My radius is 10. If I multiply these together, I get 10 over 18 pi. Okay, which is what they got, but they did it in a different order, right? They used the strict linear speed. So again, there's multiple ways to get to the same place because all of these formulas are related to each other. Okay, so if I simplify this 10 over 18, I get 5 over 9 pi. Right. So let's go to our next example. So for this example, let's find the angular speed of a pulley and a linear speed of a belt, right? So we'll have a belt on a pulley. We'll see how fast the belt is moving along the circumference of our circle, of our pulley, I guess, and we'll find how fast the pulley is turning. That's basically what we're going to do here. So we have a belt that runs a pulley. So if you think about your car, if you know anything about cars, you have lots of pulleys and they're all being spun by belts, right? Your engine turns the belts and that's what drives your tires and so forth. A belt runs a pulley of radius 6, right? So the pulley it's like a gear, has a radius of 6 centimeters and it turns at 80 revolutions per minute. So 80 times per minute is how fast it spins. Okay. We want to find the angular speed of the pulley in radians per second. Okay, so I know the revolutions, but I don't know how fast it's spinning in terms of how many angles per second, or in this case radians I should say, right, because we're not doing angles. So for this one, in 1 minute the pulley makes 80 revolutions. Okay, so in 1 minute and 60 seconds I have 80 times 360 degrees, and so I can use that to turn into radians per second. Okay, so each revolution is 2 pi radians, so 80 times 2 pi is 160 pi radians per minute. So if I want to know per second, then I need to divide this by 60 because there's 60 seconds in a minute. Okay, so my omega value, my angular speed, is 160 over 60. Now I want to be very clear here, you cannot just cancel the two 60s. It does not work that way. I can cancel the zeros and turn this into 16 pi over 6 and then reduce those two by dividing them both by 2 and get 4 pi over 3. I'm sorry, 8 pi over 3. I guess my math is off too. And that's 8 pi over 3 radians per second. Okay, so that is my angular speed of this pulley. B says find the linear speed of the belt in centimeters per second. So we're going to do something very similar. We want to find basically, we need to know the arc length, right? And the speed that is happening. So the linear speed of V of the belt is the same as that of as a point on the circumference of the pulley. So again, I know my omega, right? So remember, linear speed is really just the radius times the angular speed, right? We've seen that a few times already. So I'm sure that this PowerPoint is going to pull you in a crazy direction, which is fine. That'll, allow you to understand how these things work. But really, I can just multiply 6 times 8 pi over 3, and I will have my linear speed, right? So at the end of this, I should end up with 2 times 8 is 16 pi centimeters per second. Okay. So V is R times omega. So that's nice. Okay. They are going to use my method here. So 6 and 3 cancel to 2. 2 times 8 is 16. Right? This was from the first part. So we get 16 pi. Right? And if we multiply that out, that is 50 centimeters per second, approximately. Okay. So, example 3. Okay, we're going to find the linear speed and distance traveled by a satellite. So we want to know how fast is it moving around, okay, and also the distance. So it says here that what we've seen from other problems, that the radius of the Earth is around 6,400 kilometers. And let's assume that this satellite is about 1,600 kilometers above the surface of the Earth. So altogether, the radius that is formed is from the center of the Earth to the satellite's orbit, which is the combination of 1,600 and 6,400, right? Which is about 80 or 8,000 kilometers. So coming to this problem, it says a satellite traveling in a circular orbit 1,600 kilometers above the surface of the Earth takes 2 hours. So it takes 2 hours to go in a full rotation, right? The radius of Earth is approximately 6,400 kilometers, right? So part A wants to know, or wants us to approximate the linear speed of the satellite in kilometers per hour, okay? So, we want to know how fast it is going, so we know it takes 2 hours to do a full rotation, okay? And we know that that full rotation is 2 pi, okay? And so we want to know what is the linear speed. So remember, linear speed is S over T, right? So the time is 2 hours, and the arc length in this case is 2 pi, right? So the distance from the center of Earth is approximately R equals 1,600 plus 6,400, which is 8,000 kilometers for one orbit. Theta is 2 pi, so we're going to multiply those two values together to get our arc length. Okay, 8,000 times 2 pi. We'll divide that by 2, which is our time. Okay, so S is R times theta, which is 16,000 pi kilometers. And since it takes 2 hours to complete an orbit, the linear speed is 16,000 pi divided by 2, right? So 8,000 pi, or about 25,000 kilometers per hour. Okay. So B wants us to approximate the distance the satellite travels in 4.5 hours. So if we know that this is how fast it is going in an hour, okay, we can kind of throw this into this formula to find the distance after 4.5 hours, right? So we're solving for S here, which is V times T. My velocity is 25,000 kilometers per hour. We're doing that for 4.5 hours. And so that gets me 36,000 pi, or 110,000 kilometers. Okay. And that is how we do these problems. So hopefully I didn't go too fast for you. I'm sure that you guys were writing this down as we're going. So my next video, I'll try to be cognizant of the time and that you guys are writing these things down at the same time. I suggest you probably go through and just watch this one more time and do some of these problems on your own. I know you do have the handouts that go with them, so you'll be doing the same problems anyway, so I'm sure you will re-watch this video. So hope this was helpful. See you guys on the next video.